Have you ever wondered how cold things can actually get? I'm talking about the absolute limits of cold, where everything stops moving. Today we're diving into the mind-bending world of absolute zero, the coldest possible state of matter, where temperatures plunge to minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. So, what exactly is absolute zero? It's the point on the Kelvin scale where a system has no energy left. Theoretically, it's the point where all particle motion ceases. Sounds simple, right? But here's where it gets fascinating. We can never actually reach absolute zero. Let's explore why. Temperature measures the kinetic energy of particles in matter. The faster atoms vibrate, the higher the temperature. When atoms slow down, temperature drops. Logically, absolute zero should occur when atoms stop vibrating entirely. This concept fits nicely within classical mechanics, the collection of theories that began with Isaac Newton. Newton's laws describe how things behave on the macroscopic scale, from planets to stars to humans and our machines. However, in the early 20th century, physicists discovered that these classical theories couldn't describe behaviors at the atomic level and beyond. Enter quantum mechanics, the theory that explains how matter and energy behave at the most fundamental level. Quantum physics reveals that even at the lowest possible temperature, particles retain some kinetic energy. This is known as zero-point energy, arising from the Heisenberg uncertainty principle. This principle tells us that we can never be entirely sure of all properties of a particle. If we measure a particle's speed or energy, we can't be certain of its position, and vice versa. Thus, particles always exhibit slight vibrations, even in their lowest energy state. Let's talk about space. The temperature of space itself is about 2.7 Kelvin. Because the space between stars, planets, and clouds of interstellar dust and gas contains very few particles that interact and heat up. The average density of the universe is about 6 protons per cubic meter. Interstellar space is even emptier and colder. Yet, space's temperature remains above 0 Kelvin due to the cosmic microwave background radiation, the leftover glow from an event called the Last Scattering, which occurred about 400,000 years after the Big Bang. At this point, the universe cooled to around 3,000 Kelvin, allowing electrons to bond with protons and form hydrogen atoms, stopping electrons from scattering light endlessly. This allowed photons to travel freely, and this radiation is still detectable today. Surprisingly, the coldest place in our solar system is on the moon. There are craters at the moon's poles where sunlight never reaches, keeping their temperature around 25 Kelvin. Even Pluto's average surface temperature is about 40 Kelvin. The coldest temperature ever recorded on Earth was 184 Kelvin. In the Oort cloud beyond Pluto's orbit, temperatures may drop to around 5 Kelvin. This spherical shell of icy debris is thought to be the source of long-period comets and is loosely bound to the Sun, with objects being pulled out by the gravity of the Milky Way and other stars. And then there's the Boomerang Nebula, the coldest known place in the universe at just 1 Kelvin. Formed by gas ejected from a dying sun-like star, it cools rapidly as it expands, dropping below the cosmic microwave background temperature. Yet even these extreme temperatures pale in comparison to what scientists have achieved in laboratories on Earth, cooling matter to 38 picokelvin. Scientists pursue this to better understand absolute zero, a concept dating back to the 1600s. By 1845, Michael Faraday had cooled gases to their liquefaction points. In 1908, Heikki Kamerlingh Onnes succeeded in liquefying helium at 4.15 Kelvin, receiving a Nobel Prize in 1913, and discovering superconductivity, where certain materials exhibit zero electrical resistance at extremely low temperatures. Superconductivity, a quantum effect, becomes apparent at very low temperatures. In good conductors like gold, electrons flow well, but still scatter due to impurities, defects, and atomic vibrations, causing energy loss and heat. When certain materials are cooled enough, electrons form pairs that move freely without scattering, making the material superconducting. Superconducting magnets are used in MRI machines and particle accelerators like the Large Hadron Collider. However, these require expensive cooling with liquid helium. Research continues into finding materials that become superconducting at higher, more practical temperatures, with room temperature superconductors being the ultimate goal for energy efficiency. Let's also touch on superfluidity, another quantum effect at near absolute zero, allowing a liquid to flow without friction, seeping through cracks, and spinning indefinitely when stirred. This phenomenon occurs with liquid helium, which remains a liquid close to absolute zero. Superfluid helium atoms behave uniformly, losing individual identity and forming a collective quantum wave. Finally, the Bose-Einstein condensate, another quantum state of matter predicted in the 1920s and created in 1995, involves cooling atoms to nanokelvins, causing their wave functions to overlap and merge into a single quantum entity. This state, distinct from solid, liquid, gas, and plasma, is fragile and only possible in lab conditions. It provides insight into quantum physics, nanotechnology, and the nature of black holes and neutron stars. Notably, it allows experiments like slowing down and stopping light, demonstrating potential for quantum computing. So, there you have it, the fascinating journey into the depths of absolute zero. From the coldest corners of space to the cutting-edge research in laboratories, understanding these extreme conditions opens up a world of quantum wonders. Thanks for joining me on this chilly adventure. Don't forget to hit that like button, smash subscribe for more jaw-dropping space updates, and join us as we embark on a cosmic journey like never before.